Before we dive into this extraordinary story, if you appreciate detailed historical accounts that reveal the engineering realities behind World War II aerial combat, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. In the brutal skies over Europe during 1943, the Luftwaffe was hemorrhaging bomber crews at rates that threatened to cripple Germany's ability to conduct strategic air operations. German bomber units flying He-111s, Ru-88s, and Do-217s were suffering catastrophic losses on missions over Britain and the Soviet Union, with loss rates approaching for bombers lost for every one that American heavy bomber units were experiencing on comparable missions. German commanders attributed these losses to superior enemy fighter defenses, poor tactics, or inadequate crew training, unwilling to accept that their bombers themselves might be fundamentally flawed. But when a B-17F Flying Fortress made a forced landing in occupied France in August 1943 and was captured nearly intact, German engineers finally received the opportunity to understand what made American heavy bombers so remarkably survivable. What they discovered during months of intensive evaluation shattered their assumptions about bomber design and revealed that German aircraft reflected a philosophy that prioritized performance over survivability, a choice that was killing German aircrews at unsustainable rates. This is the story of how German engineers flew and dissected a captured Flying Fortress, how each revelation exposed another fatal weakness in German bomber design, and how they came to understand that the 4-to-1 loss rate disparity was not a matter of tactics or luck, but the inevitable result of fundamentally different approaches to keeping crews alive in combat. Before we dive into this extraordinary story, if you appreciate detailed historical accounts that reveal the engineering realities behind World War II aerial combat, please subscribe to our channel and hit the notification bell so you never miss our comprehensive documentaries. The afternoon of August 12, 1943 was overcast and tense at the Aeroprobungsstelle Airfield, north of Berlin, when Abers Friedrich Kranz received the telephone call he had been hoping for since the beginning of the American daylight bombing campaign. A Boeing B-17F Flying Fortress, damaged during a raid on the Ruhr industrial area, had made an emergency landing at a Luftwaffe airfield near Lille in occupied France. The American crew had been captured attempting to destroy the aircraft with thermite grenades and small arms fire, but alert German guards had intervened before serious damage could be inflicted. The bomber was flyable after minor repairs, and transport arrangements were being made to bring it to Rechlin for detailed evaluation. Kranz, a veteran aviation engineer who had been involved in aircraft testing programs since before the war, understood immediately the significance of this capture. The B-17 Flying Fortress had become legendary among German fighter pilots for its ability to absorb punishment that would destroy any German bomber and continue flying. Kranz had read dozens of combat reports describing B-17s returning to England with catastrophic damage, missing engines, huge holes in fuselage and wings, yet somehow still airborne and bringing their crews home safely. The statistics were undeniable and deeply troubling. Luftwaffe bomber units operating against, Britain in 1943 were experiencing loss rates of approximately 12 to 16% per mission when facing determined fighter opposition and heavy flak. American B-17 units flying comparable missions were losing approximately 3 to 4% of aircraft per mission, despite facing equally intense German defenses. This 4-to-1 disparity in loss rates meant that American bomber crews had reasonable chances of surviving their required tour of duty, while German bomber crews faced almost certain death or capture if they flew enough missions. Luftwaffe High Command had attributed these statistics to various factors, including superior American fighter escort, better American defensive tactics, and the concentration of German fighter defenses in the West while bomber forces operated on multiple fronts. But Kranz suspected the real explanation was more fundamental and more disturbing. He believed that American bombers were simply better designed to survive combat damage than German bombers, and that German aircraft reflected design priorities that had become obsolete in the face of modern air defenses. German bomber design in the late 1930s and early 1940s had emphasized speed, maneuverability, and offensive payload while accepting minimal defensive armament and protection. The Heinkel He-111, which had been the Luftwaffe's primary medium bomber since the Spanish Civil War, carried a crew of 5, could deliver approximately 4,400 pounds of bombs, and relied on speed and a handful of defensive machine guns for protection. The aircraft was designed on the assumption that its performance would allow it to evade most enemy fighters, and that missions would be conducted with friendly fighter escort when available. This design philosophy had worked reasonably well in the early war years when German forces had air superiority and opposition was limited. But as the war progressed and German bombers faced increasingly effective enemy defenses, the weaknesses of this approach became lethally apparent. He-111s shot down by enemy fighters rarely survived with repairable damage. When hit, they typically caught fire quickly due to unprotected fuel tanks. suffered catastrophic structural failures or became uncontrollable due to damage to control systems that had no redundancies. Crew survival rates from He-111 losses were distressingly low because the aircraft lacked adequate armor protection and emergency egress was difficult. The B-17F arrived at Rechlin on August 18th, transported in pieces by rail and truck convoy from France. The bomber had been partially disassembled for transport, with wings and tail surfaces removed, but the damage from combat and the crew's sabotage attempts was relatively minor. German ground crews spent 3 days reassembling the aircraft and conducting repairs, work that gave them their first close look at American heavy bomber construction. The assembly crews reported to Krantz that the quality of construction was exceptional, with precision manufacturing throughout and attention to detail that exceeded anything they had seen in German aircraft. Every rivet was perfectly formed, every panel fit precisely, every component showed evidence of careful quality control. This was mass production executed with a level of precision that German industry increasingly struggled to maintain as the war dragged on and forced labor replaced skilled workers. When Krantz first examined the reassembled B-17F, he was struck by its size and purposeful design. The aircraft was enormous by German bomber standards, with a wingspan of 103 feet and a gross weight exceeding 60,000 pounds when fully loaded. German medium bombers like the He-111 weighed approximately 30,000 pounds fully loaded, less than half the B-17's weight. This size disparity immediately suggested different design philosophies. The B-17 was designed to carry substantial defensive armament, armor protection, and redundant systems while still delivering a useful bomb load at operational altitude. German bombers were designed to deliver maximum bomb load with minimum defensive capability, accepting vulnerability as the price of offensive capability. Krantz began his detailed examination with the aircraft's defensive armament, and what he found immediately explained part of the B-17's survivability advantage. The B-17F carried up to 10.50 caliber Browning M2 machine guns positioned to provide overlapping fields of fire covering all approach angles. There were 2 guns in the nose, 2 in the top turret, 2 in the ball turret beneath the fuselage, 2 waist guns, 1 in the radio compartment position, and 2 in the tail. Each gun had substantial ammunition capacity, typically 300 to 500 rounds depending on position, giving the bomber tremendous firepower sustainability. Krantz compared this armament to a typical He-111H, which carried 5 to 7 machine guns of either 7, 92 mm or 13 mm caliber with limited ammunition and restricted fields of fire. The defensive firepower disparity was staggering. A B-17 could put up a volume of fire that was 4 or 5 times greater than a German bomber, and the .50 caliber rounds were far more destructive than the lighter German weapons. More importantly, the B-17's gun positions provided much better coverage. German bombers had significant blind spots where attacking fighters could approach with minimal risk from defensive fire. The B-17's overlapping gun positions meant that virtually any approach brought the attacker under fire from multiple guns. Luftwaffe fighter pilots had reported that attacking B-17s, especially when they flew in tight defensive formations, was extremely hazardous because the concentrated defensive fire from multiple bombers could destroy a fighter with just a few hits. German bombers flying in formation could not generate comparable defensive firepower, making them far more vulnerable to fighter attack, but defensive armament was just the beginning. Krantz's team began a detailed examination of the B-17's armor protection and survivability features, and this investigation revealed engineering sophistication that German bomber designers had never implemented. The B-17 incorporated armor plate protecting critical crew positions, with steel plates behind pilots' seats around the radio operator's position and shielding for gunners. The armor was strategically positioned to protect against the most likely angles of attack based on combat experience. More importantly, the B-17 featured self-sealing fuel tanks, a technology that had been available for years but which German bombers implemented inconsistently or not at all. The self-sealing tanks used multiple layers of rubber and other materials that would swell when exposed to fuel, automatically sealing small holes caused by bullets or shell fragments. This prevented fuel loss and dramatically reduced the risk of fire, which was the leading cause of bomber losses. German bombers typically used unprotected aluminum fuel tanks that ruptured easily and often led to catastrophic fires when hit. Oberleutnant Hans Weber, a specialist in aircraft fuel systems, conducted detailed tests on the B-17's self-sealing tanks. He fired various calibers of ammunition into fuel tanks filled with water to simulate combat damage, then observed how effectively the tanks sealed. The results were impressive and sobering. Small caliber rounds and shell fragments were sealed almost immediately, preventing significant fuel loss. Even larger caliber rounds that penetrated completely through the tank were partially sealed, reducing fuel loss to manageable levels. Weber calculated that a B-17 could sustain dozens of hits to its fuel tanks from machine gun fire, and still retained sufficient fuel to return to base, while a comparable number of hits to an Il-'s unprotected tanks would result in rapid fuel loss, fire, and probably loss of the aircraft. The self-sealing tanks alone probably accounted for a significant portion of the B-17's survival advantage, as they converted what would be fatal damage in German bombers into survivable damage that merely required post-mission repairs. The structural examination revealed even more dramatic differences in design philosophy. Major Klaus Zimmermann, Recklin's chief structural engineer, directed a comprehensive analysis of the B-17's airframe, and what his team discovered astonished them. The B-17's wing structure incorporated massive spars and ribs that provided strength far exceeding minimum requirements. The fuselage was built with multiple longerines and formers, creating a framework that could sustain damage to individual members without catastrophic failure. The control systems featured redundant cables and push rods, so that damage to one control path still left backup systems functional. The entire aircraft was designed with the assumption that it would be shot at, that it would sustain damage, and that it needed to remain flyable with significant structural damage. This philosophy was called damage tolerance, or fail-safe design, and it represented a fundamentally different approach to aircraft engineering than German practices embodied. German bombers were designed to be strong enough to handle expected flight loads with appropriate safety margins, but they did not incorporate the extensive redundancy and over-engineering that characterized the B-17. When German bombers sustained structural damage, they often suffered cascading failures where damage to one component led to failure of adjacent components, and rapid deterioration of overall structural integrity. Zimmermann noted in his report that the B-17 structural design philosophy assumed that crews were valuable assets whose lives justified extensive engineering effort to protect them, while German bomber design seemed to assume that aircraft performance was more valuable than crew survivability. This difference in priorities produced aircraft with dramatically different survival characteristics in combat. The evaluation team decided to conduct flight tests to assess the B-17's handling characteristics and operational capabilities. Oberst Kranz would conduct the initial test flight with Hauptmann Ernst Richter as co-pilot. Both were experienced bomber pilots who had flown various German bomber types in combat and in testing. On August 27, 1943, Kranz and Richter climbed aboard the B-17F for their first flight. German markings had been painted on the aircraft to prevent it from being shot down by German air defenses, and a flight plan had been filed keeping them well away from any combat zones or areas where Allied fighters might be encountered. The pre-flight checks revealed another difference from German bombers: the sheer number of systems and controls that required attention. The B-17 was more complex than German bombers, with more sophisticated engine controls, more comprehensive instrumentation, and more systems that required monitoring. This complexity was both a strength and a potential weakness. It allowed for better engine management and more precise control of aircraft systems, but it required well-trained crews who could operate the systems correctly. Kranz started the four Wright R1820 Cyclone engines in sequence, and they settled into a smooth, powerful idle. The engines were rugged radial designs that had proven reliable in service, and they demonstrated the characteristic smoothness of properly maintained American engines. Kranz advanced the throttles for takeoff and felt the B-17 accelerate down the runway. Despite its considerable weight, the bomber lifted off after a reasonable ground roll and climbed away steadily. The flight controls felt heavy compared to German bombers, requiring significant force to move, but they were responsive and harmonious. The B-17 was not nimble or maneuverable like a fighter, but it was stable and predictable, easy to fly straight and level or in gentle maneuvers. Kranz climbed to 20,000 feet and leveled off, then began a series of tests designed to evaluate the aircraft's characteristics. The B-17 flew smoothly at altitude, with good stability and no bad habits. The visibility from the cockpit was excellent, with large windows providing clear sight lines in all directions. The crew positions were spacious and well-designed, allowing crew members to operate efficiently. Kranz attempted various maneuvers, including turns, climbs, descents, and simulated single-engine operations. The B-17 handled well in all regimes, demonstrating benign stall characteristics and good control response. Flying on 3 engines was manageable, and Kranz suspected the aircraft could maintain altitude on 2 engines under some conditions. This redundancy was critical for survival, as bombers frequently sustained engine damage from flak or fighter attacks. German bombers with 2 or 3 engines could rarely maintain altitude if an engine was lost, often forcing immediate emergency landings or bailouts. The B-17's 4-engine design with powerful motors meant that losing 1 engine was survivable, and losing 2 engines might still allow the aircraft to return to base at reduced altitude. After 90 minutes of testing, Kranz returned to Rechlin and landed the B-17 smoothly. His debriefing emphasized the aircraft's remarkable stability, good handling characteristics, and the impression of rugged strength that pervaded every aspect of its design and operation. Over the following weeks, additional test flights were conducted by various pilots, and engineers continued their detailed examination of every system and component. Particular attention was paid to the B-17's engines and propellers, as these were areas where German bombers had struggled with reliability. The Wright Cyclone engines were thoroughly examined, with German engineers noting the robust construction, excellent cooling design, and sophisticated engine controls that allowed crews to manage power settings precisely for maximum efficiency or performance as needed. The engines were designed for long-range operations and sustained high power settings, requirements that Allied bombers faced routinely but which German bombers rarely encountered in the later war years when most missions were defensive operations close to German bases. The propellers were Hamilton standard constant speed units that automatically adjusted blade pitch to maintain optimal engine RPM regardless of airspeed or power setting. This automation reduced pilot workload and ensured engines operated in their most efficient range. German bombers used similar constant-speed propeller technology, but the American units were more reliable and more sophisticated in their control systems. The bomb aiming and navigation equipment on the B-17F provided another revelation about American bombing capabilities. The Norden bomb sight was a precision gyroscopic device that allowed bombardiers to aim bombs with remarkable accuracy from high altitude. German engineers had heard about the Norden sight through intelligence reports, but examining an actual unit revealed engineering sophistication that exceeded German bomb sights. The sight could calculate the complex ballistics required to drop bombs accurately while accounting for altitude, airspeed, wind, and target motion. This precision equipment enabled the American doctrine of daylight precision bombing, where formations of B-17s would attack specific industrial targets from high altitude and clear weather, aiming to destroy factories and infrastructure while minimizing collateral damage. German bomber doctrine had evolved toward night area bombing where precision was impossible, partly because German bomb sites lacked the accuracy for daylight precision attacks and partly because daylight operations had proven too costly without adequate bomber defenses. Major Hermann Göring, a distant relative of the Reichsmarschall and an experienced bomber pilot who had flown He-111s over Britain in 1940, participated in the B-17 evaluation program and provided insights from an operational perspective. Göring noted that the B-17's design reflected lessons learned from actual combat operations, with multiple features that addressed real problems bomber crews faced. The heated, pressurized crew compartments provided reasonable comfort at high altitude where German bomber crews often suffered from cold and oxygen deprivation. The crew positions were arranged to facilitate communication and mutual support. The co-pilot could assist with engine management and formation flying, reducing pilot workload on long missions. The navigator and bombardier worked closely together in the nose compartment. The engineer could monitor engines and systems while also manning the top turret gun. Every aspect of the crew interface seemed designed based on understanding what crews actually needed to perform their missions effectively. German bombers, by contrast, often showed evidence of design priorities that ignored crew needs. E-111 crews worked in cramped conditions with poor heating, inadequate oxygen systems, and layouts that made communication difficult. The aircraft seemed designed by engineers who had never spoken with operational crews about their needs. Göring stated in his evaluation report that American bomber designers understood that effective crews required good working conditions, and that investing in crew comfort and capability paid dividends in mission effectiveness. German designers seemed to view crew comfort as an unnecessary luxury, an attitude that resulted in aircraft that were harder to operate effectively on long, demanding missions. The cumulative effect of these differences was that American crews could fly longer missions in better conditions, arriving at targets less fatigued and better able to perform their bombing and defensive tasks effectively. The evaluation team conducted a series of damage tests to understand the B-17's damage tolerance in practical terms. A damaged HE-111H that had been retired from service was brought to Rechlin for comparative testing. Both aircraft were subjected to simulated battle damage using various weapons to assess their survivability. The tests involved shooting at non-critical areas with machine guns and light cannon, then attempting to fly the aircraft to determine whether they remained controllable. The results starkly illustrated the design philosophy differences. The B-17 sustained dozens of hits to wings, fuselage, and control surfaces while remaining flyable. Holes could be blown in the wing without catastrophic failure because the multiple spars and ribs maintained structural integrity. The tail surfaces could be partially destroyed yet still provide adequate control. Control cables could be severed, but backup systems still functioned. The engines could sustain damage and fail, but the aircraft could fly on remaining engines. The He-111, subjected to comparable damage, quickly became unflyable. Damage to the single main wing spar led to structural failure. Severed control cables left no backup systems. Loss of an engine seriously degraded performance and often made returning to base impossible. The test confirmed what combat statistics had suggested. The B-17 could survive damage that would destroy German bombers. Oberingenieur Carl Schmidt, who had been involved in He-111 design and was now responsible for bomber improvement programs, watched the damage tests with growing despair. He had spent years working on German bomber designs, always within constraints of weight limits, material shortages, and doctrinal requirements that emphasized offensive capability over survivability. Now he was seeing clear evidence that those priorities had been tragically misguided. The B-17 was heavier than the He-111, carried more defensive armament, had better protection for crew and systems, and still delivered comparable or superior bomb loads to targets at similar or greater ranges. The weight devoted to survival features was not wasted. It was an investment that paid returns in the form of crews and aircraft that came home rather than being lost on every mission. Schmidt wrote in his evaluation report that German bomber design needed fundamental reorientation toward survivability, but he acknowledged that implementing such changes would require years of development, time and resources that Germany no longer had. The evaluation program also included an extraordinary exercise where the captured B-17F was flown in formation with German bombers to compare formation tactics and defensive capabilities. On October 3, 1943, the B-17 flew in a formation exercise with 3 He-111H bombers. The aircraft flew at 22,000 feet in a simulated combat formation while Bf-109 fighters made mock attacks using cameras rather than weapons to record their approaches and simulate firing. The exercise was monitored by observers on the ground and in chase aircraft, and the results were documented extensively. The findings were unambiguous and profoundly depressing for German observers. The B-17's defensive armament provided far better coverage than the German bombers, forcing the mock-attacking fighters to approach from disadvantageous angles or face heavy simulated defensive fire. The B-17's armored crew positions meant that attacks that would kill or wound German bomber crews would leave the B-17 crew operational. The self-sealing fuel tanks meant that attacks setting German bombers ablaze would merely damage the B-17 without fatal results. When the simulated attacks were analyzed, observers calculated that in an actual combat situation with real ammunition, all 3 He-111s would probably have been shot down, while the B-17 would likely have sustained damage but remained airborne. The formation exercise also demonstrated the effectiveness of American defensive tactics. American B-17 formations flew in tight boxes that allowed mutual defensive fire support, with dozens of heavy machine guns able to concentrate fire on attacking fighters. German bomber formations were looser and could not generate comparable defensive firepower. The discipline required to maintain tight formations was considerable, requiring excellent pilot training and formation flying skills. But the defensive benefits justified the effort. German bomber formations that had attempted similar tight formations found them difficult to maintain and had generally adopted looser formations that were easier to fly but provided less mutual support. The Americans had invested heavily in pilot training to develop the formation flying skills necessary for their defensive tactics, while German training programs had been shortened and reduced as the war progressed in pilot replacement. Needs exceeded training capacity. Hauptmann Richter, who had served as co-pilot on several B-17 test flights, conducted extensive interviews with the captured American crew members who had flown the aircraft before its emergency landing. The Americans were held at a POW interrogation facility and were reluctant to provide information beyond name, rank, and serial number as required by the Geneva Convention. However, Richter was able to glean some insights from careful questioning and observation. He learned that American B-17 crews received extensive training before deploying to combat, with crews training together as units and practicing all aspects of their mission, including formation flying, bombing runs, and defensive procedures. This crew-based training created cohesive units where members understood each other's roles and could work together effectively under stress. German bomber training had become increasingly individualized and abbreviated, with crew members often meeting their teammates only upon arrival at operational units. The result was German crews that lacked the cohesion and practiced coordination that characterized American B-17 crews. The final comprehensive report compiled by Eberst Krantz and his evaluation team was completed in November 1943. And distributed to Luftwaffe High Command, the Reich Air Ministry, and bomber unit commanders. The report was brutally honest about German bomber deficiencies and made uncomfortable comparisons with American practices. The executive summary stated clearly that the Boeing B-17 Flying Fortress represented a fundamentally different approach to bomber design than German aircraft embodied, an approach that prioritized crew survivability and mission completion over maximum offensive performance. The B-17's defensive armament, armor protection, self-sealing fuel tanks, redundant control systems, damage-tolerant structure, and crew-focused design combined to create an aircraft that could sustain damage fatal to German bombers and continue flying. The report calculated that the 4-to-1 disparity in loss rates between German bombers and American B-17s was primarily attributable to these design differences rather than to tactical or training factors, though those also contributed. The report made specific recommendations for improving German bomber survivability. The highest priority recommendation was immediate implementation of self-sealing fuel tanks on all bomber aircraft, as this single modification could dramatically reduce losses from fire, the leading cause of bomber casualties. The report recommended increased defensive armament, particularly additional weapons covering previously undefended approach angles. Better armor protection for crew positions was recommended, acknowledging that this would increase weight and reduce performance but arguing that bringing crews home alive was more valuable than marginal performance advantages. The report recommended redesigning cockpit layouts and crew positions based on input from operational crews rather than purely on engineering convenience. Finally, the report recommended fundamental changes to bomber design doctrine, shifting from emphasis on offensive capability toward balanced designs that integrated offensive capability with comprehensive survivability features. The report acknowledged that most recommendations could not be implemented quickly. Redesigning and re-engineering existing bomber types would take months or years, and Germany's industrial situation was deteriorating as Allied bombing intensified. Material shortages, particularly of rubber for self-sealing tanks and aluminum for additional structure and armor, limited what could be accomplished. The recommendation to develop entirely new bomber designs incorporating lessons from the B-17 evaluation was particularly unrealistic given Germany's situation. By late 1943, Germany was increasingly focused on defensive fighter production rather than bomber development, recognizing that the immediate threat was Allied bombers attacking Germany rather than German bombers attacking enemy targets. The strategic situation had shifted fundamentally, with Germany forced into a defensive posture where bomber development was no longer a priority. Nevertheless, some limited improvements were implemented based on the B-17 evaluation. Self-sealing fuel tanks were retrofitted to some German bombers, though the program was incomplete and inconsistent across units. Additional defensive armament was added to He-111s and other bombers, often at the initiative of individual unit commanders rather than through systematic programs. Some armor protection was added to crew positions, though not to the extent the evaluation report recommended. These modifications helped somewhat, but they were incremental improvements that could not fundamentally transform aircraft designed with different priorities. The basic problem remained. German bombers were designed for an earlier era of warfare when opposition was limited and offensive capability was paramount, while American bombers were designed for sustained operations against heavy opposition where survivability was essential. The 4-to-1 loss rate disparity between German bombers and American B-17s persisted throughout the remainder of the war, though German bomber operations decreased substantially as the Luftwaffe focused resources on defending against Allied air attacks. German bomber units continued suffering heavy losses on the missions they flew, with crews understanding they faced poor odds of survival. Bomber crew morale declined as losses mounted and as crews recognized they were flying obsolete aircraft against modern defenses. Many experienced bomber crews were eventually transferred to fighter units or to training commands where their skills could be better utilized. The Luftwaffe's bomber force, which had been a powerful offensive weapon in 1940, had by 1944 become a wasting asset that high command committed to operations reluctantly and with recognition that losses would be severe. American B-17 operations over Europe, by contrast, intensified throughout 1943 and 1944 despite significant losses to German fighters and flak. The 8th Air Force and later the 5th 10th Air Force flew increasingly large formations of B-17s and B-24 Liberators against strategic targets across Germany and occupied Europe. The bombers sustained heavy losses during 1943, particularly on missions beyond fighter escort range, with some raids losing over 20% of participating aircraft. But the introduction of long-range fighter escorts, particularly P-51 Mustangs, in early 1944 shifted the balance decisively in favor of the bombers. Even during the costly raids of 1943, American bomber losses as a percentage of sorties flown remained substantially lower than comparable German bomber losses, validating the B-17's survivability advantages. By 1944, with fighter escort available throughout missions and with German fighter defenses increasingly degraded, American bomber loss rates declined to sustainable levels while the volume of bombs delivered to German targets increased exponentially. The post-war period brought additional perspective on the B-17 evaluation and its findings. German engineers and officers who survived the war were extensively debriefed by Allied intelligence teams. Oberst Kranz, who had led the evaluation program, provided detailed testimony about his findings and their implications. He stated that examining the B-17 had been one of the most educational and depressing experiences of his career. Educational because it revealed sophisticated engineering solutions to bomber survivability challenges. Depressing because it made clear how far behind Germany had fallen in bomber design and development. Kranz noted that the B-17 represented integrated systems engineering at its finest, with every component designed to work harmoniously with every other component to achieve the overall mission of delivering bombs accurately while protecting the crew. German bomber design had never achieved this level of integration, instead producing aircraft that were compromises between conflicting requirements with inadequate attention to crew survivability. Major Schmidt, the He-111 designer who participated in the evaluation, provided particularly candid assessments of German bomber design failures. He acknowledged that German designers had known about self-sealing fuel tanks, armor protection, and defensive armament requirements, but had consistently prioritized performance over protection due to weight constraints and doctrinal preferences. He noted that German bomber doctrine had assumed air superiority, or at least air parity, conditions where lightly defended bombers could operate effectively. When those assumptions proved invalid and German bombers faced heavy opposition, the design deficiencies became fatal flaws. Schmidt stated that if he could redesign German bombers from the beginning with knowledge he gained from the B-17 evaluation, he would have accepted lower performance to achieve better survivability, recognizing that slower bombers that returned home were more valuable than faster bombers that were shot down. The captured B-17F that had been evaluated so thoroughly at Rechlin met an ignominious end in early 1945. As Allied forces advanced into Germany and the military situation became desperate, the bomber was destroyed by German personnel to prevent its recapture. By that time, the lessons from its evaluation were largely academic, as Germany's bomber force had been reduced to insignificance and the war's outcome was no longer in doubt. But the evaluation report survived and provides fascinating insights into how German engineers viewed American bomber technology and their own aircraft's shortcomings. The report stands as a remarkable example of honest technical assessment that did not attempt to minimize uncomfortable truths or rationalize away evidence of German inferiority. The broader implications of the B-17 evaluation extended beyond bomber design to fundamental questions about military technology development and the relationship between design philosophy and combat outcomes. The B-17 embodied an approach to weapons system design that recognized crews as valuable assets worth protecting through extensive engineering effort. The aircraft accepted weight penalties and performance reductions to incorporate survivability features, based on calculations that bringing crews home alive was strategically more valuable than marginal improvements in speed or bomb load. German bomber design reflected different priorities, emphasizing offensive capability and assuming that superior German tactics and crew quality would overcome any deficiencies in aircraft protection. This assumption proved tragically wrong, and the 4-to-1 loss rate disparity was the quantitative measure of that error. The evaluation also highlighted the importance of combat experience in driving design evolution. The B-17 underwent continuous improvement throughout its production run, with lessons from combat operations systematically incorporated into new variants. The B-17F that German engineers evaluated represented years of iterative refinement based on operational feedback from crews who had flown combat missions and survived to report what worked and what needed improvement. German bomber development had largely stagnated after initial deployment, with few significant improvements implemented because resources were diverted to other priorities and because Germany's deteriorating strategic situation left little capacity for systematic improvement programs. The result was that American bombers evolved to become more effective, while German bombers remained essentially unchanged from their 1930s designs. The story of the captured B-17 evaluation provides insights into the human dimension of engineering and military technology. The German engineers who examined the Flying Fortress were highly skilled professionals who understood aircraft design thoroughly and who could recognize excellence when they saw it. Their evaluations were honest and technically sophisticated, acknowledging American superiority without attempting to rationalize or excuse German shortcomings. These engineers understood that they were examining an aircraft whose design philosophy was simply better suited to the realities of modern air warfare than the philosophy underlying German bombers. Their reports communicated this understanding clearly to military leadership, though that leadership lacked the resources and time to act on the recommendations effectively. For the bomber crews on both sides, the design philosophy differences translated directly into survival probabilities. American B-17 crews faced terrible dangers from German fighters and flak, and thousands of American airmen were killed or captured during bombing operations over Europe. But the B-17's survivability features gave them substantially better chances of surviving mission after mission compared to German bomber crews flying aircraft without comparable protection. The statistics were clear. American bomber crews who completed their required 25-mission tour had roughly 50% survival rates during the costly 1943 period, improving to over 70% in 1944 as defenses improved and losses declined. German bomber crews operating over Britain or the Soviet Union faced much worse odds, with survival rates that made completing extended operational tours increasingly unlikely as the war progressed. The psychological impact of flying bombers with fundamentally different survivability characteristics was significant and affected crew performance and morale. American B-17 crews gained confidence in their aircraft's ability to bring them home despite damage, and this confidence helped them maintain discipline and effectiveness even when sustaining heavy battle damage. German bomber crews increasingly understood they were flying death traps where a single hit in the wrong place could result in catastrophic fire or structural failure, and this knowledge affected morale and effectiveness. Crews flying aircraft they believed could not protect them adequately often became fatalistic or desperate, and their performance suffered accordingly. One of the most poignant aspects of the B-17 evaluation story is the sense of opportunity loss that permeates the German engineering reports. The evaluation team's findings made clear that Germany had possessed the technical knowledge to design survivable bombers, but had made strategic and doctrinal choices that emphasized different priorities. The self-sealing fuel tank technology that so impressed German engineers was not particularly complex or exotic. It was straightforward engineering that required materials and manufacturing capacity Germany possessed. The armor protection, redundant control systems, and defensive armament arrangements that made the B-17 survivable were all within German engineering capabilities. What Germany lacked was not technical knowledge, but the doctrinal insight that investing in survivability would pay strategic dividends by preserving trained crews and maintaining bomber force effectiveness over time. This lack of insight resulted in design priorities that killed German aircrews unnecessarily. As we conclude this detailed examination of how German engineers examined a captured B-17 Flying Fortress and came to understand why their bombers suffered 4-to-1 loss rates compared to American heavy bombers, several themes emerge with particular clarity. First, design philosophy and priorities directly determine weapon system effectiveness in ways that cannot be overcome through tactics or crew skill alone. The B-17's survivability advantages stemmed from conscious design decisions to prioritize crew protection, and those decisions resulted in an aircraft that could operate effectively in conditions that would destroy German bombers. Second, honest technical assessment is essential for identifying weaknesses and opportunities for improvement, even when such assessments reveal uncomfortable truths about your own equipment's inadequacy. The German engineers who evaluated the B-17 provided their leadership with clear, honest information about German bomber deficiencies, though circumstances prevented effective responses. Third, industrial capacity and engineering sophistication manifests not just in isolated technological breakthroughs, but in the consistent execution of sound design principles across entire weapon systems. The Boeing B-17 Flying Fortress earned its legendary status through combat performance that validated its designers' philosophy of comprehensive crew protection and mission survivability. The aircraft could absorb punishment that would destroy other bombers and continue flying, bringing crews home alive to fly another mission. German engineers who examined the B-17 in detail recognized this excellence and understood how far their own bombers fell short of this standard. Their honest evaluations documented the 4-to-1 loss rate disparity and explained its causes in terms of specific design differences, providing their leadership with information needed to address the problem. That the information came too late, and in circumstances where effective action was impossible, reflects Germany's broader strategic situation in the war's latter years. Thank you for watching this comprehensive exploration of how captured American bomber technology revealed the engineering reality behind devastating loss rate disparities. If you found this detailed technical and historical analysis valuable and engaging, please subscribe to our channel for more in-depth documentaries examining the engineering, decisions, and human experiences that shaped World War II. Share this video with others who appreciate thorough military history that explains not just what happened but why it happened through detailed technical analysis. Leave your thoughts and reactions in the comments below, as we value our community's engagement with these complex historical narratives. Your support enables us to continue producing these detailed examinations of military technology and the lessons they contain about design philosophy, engineering excellence, and the human cost of technological choices. Until next time, this is the story of how examination of enemy technology revealed uncomfortable truths about design priorities and their consequences, and how the B-17 Flying Fortress became the bomber that could survive what would destroy its contemporaries through engineering. Excellence focused on the fundamental mission of bringing crews home alive.